This time, let's talk about the distance between complex points. We are given here with three different complex numbers, and later on we're going to plot them on this Argand diagram, and later on we're going to solve for distances between them. Now, let's talk about distance between complex points. Actually, we will have the same formula as the distance between real numbers or our points on the Cartesian plane. That is because if we talk about generally, say for example, if you have a general z sub 1, not necessarily this z sub 1 here, which we express as x sub 1 plus I y sub 1, and we'll say z sub 2 being x sub 2 plus I y sub 2, okay, we can actually talk about the difference between them, okay, as the distance, okay, or we're talking about this one here, the modulus between the difference between them, equivalent to the square root of the squares of the difference of the components. For the real part, you have here x sub 1 minus x sub 2 squared, or you can just interchange them, that's still okay, plus you have here y sub 1 minus y sub 2 squared. Notice, in this formula, we did not place here our i's. We simply use here the coefficients of our imaginary part. And this is a similar formula with the basic distance between 2 points in the real Cartesian plane. Now, for the complex points, similarly, but of course, the graph of this would depend on the components as well. So for our z sub 1, it's actually z sub 1 here. Our x, or the real part, is negative 4. Our y is the imaginary part, or the coefficient of the imaginary part, that's 3. For x sub 2, you'll have 2. You have here positive 5. And for x sub 3, you will have, or for z sub 3 rather, you have negative 8 and negative 1. So you can see the complex points here for our z sub 1 at negative 4, considering that each grid here is actually by 1, and positive 3. This is the location for our z sub 1. Okay? We also were able to identify the polar form of this using identifying the modulus of the said point, and then the angle intended for that. Okay? But that's not the concern here. For our z sub 2, it's actually a 2 and then 5. Okay? So this is our z sub 2. So if you're going to solve for the distance between z sub 1 and z sub 2, it's still the distance of this length here. That's actually a line segment connecting the 2 points. So basically, we're just using the same formula. Now let's plot, let's identify the distance between them. So for z sub 1, here, z sub 1 is negative 4. And then our x components. So you have here negative 4 minus 2 squared, plus for our y, 3 minus 5 squared, if I'm correct. Okay, you will have here the square of negative 6 plus the square of negative 2. So you will have the next part here, square root of 36 plus 4. So you will have here the square root of 40, or in simplified form, you will have here 2 square root of 10. This is the distance between the points, complex points, z sub 1 and z sub 2, indicated by this formula here. Again, we have the same formula as the original distance formula for the Cartesian plane involving real numbers. Okay, now let's plot z sub 3 here is at negative 8, negative 4, 5, 6, 7, 8, and negative 1 here. So if we're going to solve for a distance between z sub 1 and z sub 3, assuming that my lines there are straight, so again, you're talking about the length of the line segment connecting the 2 points. So for that, for our z sub, let's have it here, z sub 1 and z sub 3, it's actually like this one. Again, as mentioned, you can interchange them because they will just be under the same square root here, as long as you will have your x sub 1 minus x sub 3, okay, squared, plus y sub 1 minus y sub 3 squared. The components for our z sub 1 is r, negative 4 and 3. So you have here negative 4, the other one 3. And then you will have your 8 and negative 1. So minus 8, then minus negative 8. Take note of that. Minus negative 1. Please don't forget, it will happen, the double negative property will be applied here. That's actually negative 4 plus 8, 3 plus 1. So you will have here 4, the square of 4, and the square of 4. That's 16 plus 16, square root of 32, or again, you will have here 2 square root of, that's 4. 16 times 2. So you have 4 square root of 2. This is the distance between complex points z sub 1 and z sub 3. Now, let's try to complete this by getting the distance of the line segment connecting these two. Hopefully, I can do this right. Okay, I can't, so let me try again. So we have to solve for the length of the line segment connecting z sub 2 and z sub 3. So you will have here z sub 2, z sub 3. That's actually the modulus of z sub 2, minus z sub 3, indicated by the distance formula here, x sub 2 minus x sub 3 squared, and the square of y sub 2 and y sub 3. So you will have here the square root. X sub 2, that's 2 and 5, so don't forget about that. 2 minus negative 8, don't forget this is actually for our z sub 3, plus 5 minus negative 1 here, negative 1 squared. So you have here the square root of 2 plus 8, and then you have here 5 plus 1. So this is actually 10 squared plus 6 squared. You'll be given with 100 plus 36. That's the square root of 136. I believe it's divisible by 4, so that's 25 plus 9. That's actually 4 times 34, so 2 square root of 34. This is again for the distance between complex points z sub 2 and z sub 3. So basically, this is how we solve the distance between complex points. Similar formula with the distance between points in the Cartesian plane. Thank you very much for watching.